I feel like I should do something while we wait for everybody else to get here. Should we just start? If they're not here early, they're late. Is that a thing, right? That's a thing, right? If you're not early, you're late. Like, oh, we could play hangman. I don't know. I feel like that would just be an empowering you to consider lynching the professor. So we'll skip the hangman for today. Oh, could we play hangman with only manufacturing words? We'll get started in just a second here. Did anybody else not make it? Oh. Did anybody else almost not make it this morning? Because you guys almost got a video this morning. I got 1 minute left. Yeah, so I have a chronic shoulder injury, chronic pain in my shoulder. Been there 10 years. First doctor diagnosed it as a repetitive stress injury. And it was funny because when he said you could get it from a single motion of doing this, I just started laughing. And he said, like, do you remember the incident? And I did, but it wasn't a single incident. It was thousands of, maybe hundreds, thousands, probably exaggeration. It was hundreds of times when I was diving between the students, trying to hit the emergency stop switch because the machine tool was making a noise I didn't like. You know what, though? Shoulders are expensive. I stopped diving between the students as soon as he told me that. The machine can crash. Now I just say, hey, hit the e-stop. But so anyway, so I had this chronic shoulder injury. Back in 2019, I really didn't feel good. And it would act up and it would go away. But I had this pain all down my right arm. And I spent 4 days on WebMD Googling, chronic arm pain. But cross off all of the tick marks that say it's a heart attack, because it's not a heart attack. I just have a problem with my shoulder. On the 4th day, I went to the hospital, and of course, it was a heart attack. Now, you can't call the doctor's office without getting sent to the emergency room. So I spent 7 hours in the ER yesterday so that I can get an appointment to have somebody look at my shoulder. So I wasn't sure they were going to let me out. Normally, that's a 3-day trip. I know this because I've had several of those 3-day trips. So don't hurt your shoulder. That's my advice to you. But do press the e-stop. And you don't have to reach so far if you're the person standing next to the machine. You can just do this. And I have actually done that many times to stop the machine tool. So, right. But you didn't get just served up a video today because they let me go at 9 o'clock last night. And said, you should get an appointment for your shoulder. And I said, that's what I was trying to do. I was calling the doctor's office to get an appointment for my shoulder. Okay, we're here. It is time to start, right? Does anybody remember what we're talking about today? Anybody know? Quick, shout it out. Okay, manufacturing metrology. Before we start with manufacturing metrology, let's start with metrology overall, though. So what do I mean when I say metrology? And I know this. I have a PhD in metrology.
The ology
The ology, but for measuring things, right? I suppose metrology, in the etymological sense, is the study of measuring things. But that's not what we mean when we say manufacturing metrology, is it? No. We just mean measuring stuff. We just, since it's a university class, we can't say manufacturing measuring stuff. We have to call it metrology. It's just like over here, you don't have lab in a machine shop, do you? Did you know this? It's not a machine shop. It is a manufacturing laboratory, because laboratories have way more status on campus than shops do. So it's a manufacturing laboratory, regardless of all the machine tools inside. So there's a lot of stuff in names. Names are important. No, they're not. But they totally make people feel important. All right, so measurement, right? We're going to talk about measuring stuff. Now, we talk in this class about manufacturing engineering. We talk in this class about manufacturing science. And so as we get into this talk about measurement, why is it that scientists would measure something? We've talked about the difference between science and engineering before. Why is it that scientists measure something? Yes? All right, so let's stipulate that we can't do science without measuring something. What is the purpose of the measurement in the science? Yep. Okay, so we've got our independent variables. Those are the things we choose, and we want to measure those to make sure that we actually got the thing that we chose. And we'll measure the dependent variables. Those are the results of choosing the independent variables. But the reason we do it as scientists is because we'd like to find out the answer, right? If it's science, we always joke as grad students, we would say, if we knew the answers, it wouldn't be research, right? So you should be asking questions that you don't know the answer to when you're actually doing science. Now, as an engineer, or as a manufacturing engineer specifically, but just in general as an engineer, why do I want to measure things? Yeah.
Certain manufacturing needs to meet certain requirements, but
so we've got predefined requirements, and so as a scientist, we're measuring to understand why something happens. As an engineer, we're often measuring to control how something happens. Does that make sense? So we're making our measurements, we're making our in-process measurements especially, right? We talked about quality. We said we'd rather control the quality than inspect the quality at the end, right? There's really no value in the inspection of quality at the end, but if we can not make any bad parts, that'd be good. So we do our measurements in process, make sure we don't ship any bad or create any bad parts to ship. That's a better thing. So as engineers, we're often measuring to make sure that we can control things. Does that make us control freaks? I think it does make us control freaks, but that's okay, because it's a room full of control freaks. How could that go wrong? All right. So anybody remember who Lord Kelvin was? I guess he passed away back in the, actually, I know the date here. He passed away in 1907. Anybody remember Lord Kelvin? No? So he was actually the first British scientist to be knighted, I think, for his science ability. Maybe I got that wrong, but there's something, you can look it up on Wikipedia, it's there. But Lord Kelvin, where does the name sound familiar? Does the name sound familiar? Yeah, there's a scale, right? A Kelvin scale. So Kelvin is the one that determined absolute zero with the highest precision back when they were trying to figure out absolute zero. And therefore they named the scale after him. But he says to measure is to know. So Kelvin was a scientist, right? And he wanted to find out things by measuring. But he also understood engineering. He said if you cannot measure it, you cannot improve it. Right? He goes on, he says, when you can, all right. When you can measure what you're speaking about and express it in numbers, you know something about it. When you can't measure it, you cannot express it in numbers. Your knowledge is of a meager and unsatisfactory kind. Is that enough? Are we done with metrology now? Yep. Kelvin's a pretty smart guy. He also has been quoted as saying that X-rays will be found to be a hoax. So he may not have hit everything on the nose. All right, there's a way to advance this slide without turning on the video. But I don't know what it is. So we'll just press twice. The video will start. Then the slide will advance. All right, so as engineers, when we're doing our metrology, when we're doing our measurement, we're doing it because we want to control stuff, right? As engineers, we're doing our metrology, we're doing it because we want to control something. And we get our statistics like this. And so we remember we talked about quality engineering, we talked about the different sigmas, and we'd like to have all of our, so if our tolerances are in this range, then we can always make the parts and things like that, right? Does that make sense? So as engineers, we're going to make our measurements and we're going to use statistics. We do need to be careful with statistics. What's immediately wrong with this statement? They haven't been teenagers for 5 years already. All right. I had to throw a little humor in there, right? So we're trying to understand things as scientists. And so we talked about accuracy and precision previously, right? And so precision is how close together we're able to hit the target. And accuracy is how close to the aiming point of the target we're going to, or we're getting, right? So how does this concept impact us when we're doing measurement? So how does this understanding of precision and accuracy important to us as engineers doing measurement? Or as scientists, doesn't matter. Yes?
Are you talking about the accuracy and precision of the measurement itself or the thing that we're measuring?
Yes, that is the question. So are we talking about the accuracy of the thing that we're measuring? So how well is the thing made? How closely does it hit the tolerances? Or are we talking about the accuracy of the measurement that we used to check to see if it has hit the tolerances? And so as we talk about this, mute. As we talk about this, so when we're making stuff, right, we know that we can't make stuff perfectly every time. We know that there's going to be some variation in the things that we make. And so let's just say we're simply making a round piece. This is round as long as it's projected on the board, right? All right, we're making a round piece. The diameter is 0.75 inches plus or minus 0.001 inches. That's fairly straightforward, right? We could make that diameter. We all know how to make that diameter. It might take us a couple tries, but we know how to do it. And let's say it's going to be 3 inches long plus or minus 0.01. Right? I don't really care about the length. I do care about the diameter. That's pretty clear? So when we make these, if we just measure them as they come off, if this is our nominal, 0.75, and we know from making our control charts, we'll have some scatter in the data. And maybe we'll see a trend up here, and that's telling us that the tool's wearing out or something like that. As we do this, we'll get some data like this, right? Here's what I also know. If I take one of them, so this is maybe n equals 1,000 parts. If I take one of them and I make my measurement, I'll get that point, right? What if I take the same one and I measure it again? And I get this point. And then what if I take it and I measure it again? and I get this point. And I take it, I measure it again, and you get the pattern, right? So there's uncertainty in our part from part to part variability, but there's uncertainty in our measurement. Now, why do we have uncertainty in our measurement? Yes?
You can only measure so small.
So we can only measure so small. So we have a limit on the resolution of our measurement tool. Yeah, actually, one way to get this variation to go down is to reduce the resolution of your measurement tool. When the measurement tool has more resolution, you'll end up with more variation at this end. Does that click? Do you know why? So let's think of it digitally. So if you got a digital caliper, you guys have used digital calipers in the lab? How many decimal places do they output? Anybody remember? Pretty sure those go out to, so some number of inches, 0.1, 2, 3, and then it was either a 0 or a 5 over here, right? So 3.5 decimal places, right? According to that. That's how many decimal places the little digital circuit board is outputting to the screen. You know what the limit on that is? The size of the screen and the size of the numbers they put on the screen. If they had a longer screen, they could put out more decimal places. Imagine they're doing floating point math there. There's a CS guy that usually sits over here. He's not here. How many decimal places in a floating point number can you get? It's like 14 or something like that. You can get a lot of decimal places in a floating point number. So you can put a lot of decimal places out. That's pretty cool. Except the ones out here have no meaning if you're just putting out decimal places, because our ability to make that measurement is limited by the physics of the little machine, the little caliper that you're using to do that with, right? So if I limit this to only put out one decimal place, it will always give me the same number if the caliper itself is able to measure out to 3 decimal places. Does that make sense? But if the caliper is able to measure out to maybe let's give them the 3.5 decimal places. If it's able to measure out to that, then I'm going to get a lot more variation in the last couple decimal places on my part. So I will have a higher perceived uncertainty with a higher resolution device. The uncertainty is really the same regardless of our perception of it, I think. Okay, so we have measurement uncertainty and we have part-to-part variation. So those are things that we really got to consider when we're making our manufacturing measurements. Let's change the title of this lecture. Measuring stuff in manufacturing instead of manufacturing metrology. Sounds way too uppity. This morning, one of my good friends and colleagues had sent me a copy of an abstract he had written for a paper he wants to submit to go to a big conference over in Europe. And even I was amazed at the excessive use of ginormous words. And I think I know what he was saying. I'm pretty sure I know the meaning of all the words he used. But it was like 4 paragraphs just chock full of words that I don't think any of the words had less than 7 syllables. So sometimes as scientists and engineers, we try to make ourselves feel smart by using big words. But it's really our inability to make the parts to the same size and our inability to measure the parts. And so this measurement is called measurement uncertainty. I think that's a fair term, right? That's not too many syllables. And you can read the gum to understand measurement uncertainty. The GUM is, well, scientists and engineers like our TLAs, right? Our 3-letter abbreviations. The GUM is the guide to measurement and uncertainty. And it's put out by NIST, the National Institute of Standards and Testing here in the US. Technology testing. Who knows? I talk to people at NIST and they can't even tell me what it is. It's technology. Did you work there? Yeah. See, I could have asked you. Well, maybe she doesn't know what it means. Maybe I'm right. She's wrong. There's uncertainty. Okay. As a manufacturing engineer, as a manufacturing metrologist, what is it we want to measure? So we want to measure dimensions on our parts, right? We can measure length. We can measure. I'll just do this one. So we can measure length, angle, flatness, roundness, diameter, form. What else could we measure? If we're controlling our manufacturing process, what else could we measure? These are the ones that jump right out at us, right? Length, angle, flatness, roundness, diameter. What else could we measure if we're controlling our manufacturing process? So we could measure material qualities. And if we're the manufacturer, we might want to measure that on the incoming material to make sure that we're actually getting the material that we purchased. But we may be the material manufacturer, in which case we're going to measure the outgoing material to make sure we're giving our customers the correct stuff. And as the manufacturer, we may need to measure those material properties after we process it because our process might change them. So yeah, material properties, so strength, hardness, percentages of different alloying elements in the material. Those are all things that we may need to measure. What else could we measure? Yep. Weight. Weight's not on there? No, it's not. Weight. What else could we measure? What else would we measure in manufacturing? Color. You can measure color. Length, angle, flatness, roundness, diameter, form, weight, color. Anything else that comes to mind? Well, basically, you can measure anything that you can put a tolerance on, right? You can measure anything that you could specify in some way where you can put a tolerance on it. And you can build a device to measure it. Anybody ever measured color before, actually? You have? How did you measure color?
There was a machine. I think it shot a laser and then it measured how much was reflected to figure out the wavelength.
Oh, that's a cool way to measure color. There are cheaper ways to measure color. I actually, as a grad student, built a colorometer, a colorometer. Like I was getting into the big words at that point, I suppose. But it was a box. The inside of the box was painted flat black. There was a gray card of known color in the bottom of the box. There was a camera on top. And we controlled the wavelength of light that was illuminating the thing that we would put in there. We used that gray card to calibrate it. And then used image processing software. I think I used, some image processing software to then look at stuff. And it was like magic. We were doing it. Why were we measuring color? I remember. To study blooming on chocolate. You guys have eaten chocolate? Have you ever had little white powdery stuff on the outside of your piece of chocolate before you ate it? So chocolate is an emulsion. It's not like a mixture. It's not chemically bonded. And so that's fats and sugars coming out of the emulsion and coming to the surface. So you can still eat it, but it doesn't taste as good and it totally doesn't look as good, right? Like if you open up that chocolate bar and it's all white on the top, you may or may not take a bite out of it. Yes, this research was funded by chocolate manufacturers to try to develop chocolate formulas that did that more slowly so their chocolate would have a longer shelf life, but still had to taste good. So we were actually aging chocolate. We made a heat treating furnace for chocolate. It involved a refrigerator and a light bulb. And we would vary the temperature over time because that's the cycle that causes that. And then we would put it in our little color measuring box to see how much blooming had occurred. It's like amazing, amazing. So you can measure all kinds of different things, but that was science, not engineering. So we can measure dimensions, and we can measure things like color and things like that. What else do we really care about? One of the things we put on the board yesterday as things we need to know as a designer, and we need to tell the manufacturer. So we had 5 things on the board. One of them was function. So there's really 4 things we put on the board yesterday. What's the other thing we want to measure? Oh, different measuring tools. We could measure all these other. Oh, see, yeah, there was a slide about this. Roughness, electrical, chemical, magnetic, microstructure, stiffness, hardness, ductility. What is roughness? What is roughness on a manufactured part? Yep. The surface finish, okay. So take your thumb, everybody. The desk in front of you, there's 2 parts of the desk, right? There's a wooden part and a plasticky part. Rub your thumb back and forth across the plasticky part. Now rub it back and forth across the wooden part. With your eyes closed, could you tell which one it was later? Right? You've just comparatively measured those 2 surfaces with your thumb. Is that a good way to measure surface roughness? Well, what if I had a set of different roughness samples and I'd try this one and then try the surface I'm trying to measure? So I've got my calibration standard. Let's say this is my calibration standard, and I go, yeah, the table's rougher than my calibration standard, so I have a data point, right? If I had 2 of these different calibration standards, maybe I would get this one. Now I can tell you that the table is in between these 2 calibration standards. So wait a minute, I could measure the roughness of the table with my thumbnail. In fact, that is a valid way to measure roughness, and it is used all over the world in industry today to check parts as they come off of a manufacturing process. Last I knew, that's the metric that the Navy uses when they're qualifying weld roughness in nuclear submarines, because you can calibrate that thumb pretty well. Actually, you can feel about a 10,000th of an inch difference if you rub across a deviation in height of about a 10,000th of an inch difference with your thumb. Now, is this the best way to measure roughness? How else might we measure the roughness of a part? And so the roughness is how much it goes up and down in a space. Let's just say it's how much it goes up and down in a space. All surfaces have geometry, right? They all have a shape, and they all have roughness. All surfaces have geometry and roughness. In fact, all manufacturing processes are about putting surfaces with specific geometry and roughness in specific locations. That's what all manufacturing processes do. So how else would I measure roughness if I'm not going to use my thumbnail? Because I can totally do it with my thumbnail. And we've done it that way since the first caveman talked to the second caveman about how rough a stone was. That's how we've been measuring roughness, tactile measurement with our fingers. We could use a microscope. The first people that started writing papers about measuring roughness were using a microscope. There's a German scientist, I can't remember his name, but he took his microscope, and who's ever looked through a microscope? So as you move up and down, the focus changes. And so at a certain height, if you have a rough sample, some of it's in focus and some of it isn't, right? And so what he would do is at a height, he would sketch how much of it was in focus on his little paper, because this was before we had cameras and stuff and microscopes. So he'd sketch that out. They would come up a known amount because he had a calibrated vertical stage. He'd come up a known amount and then see how much of it was in focus. Come up a little bit, see how much of it was in focus. And so he could figure out an average roughness of the part by how much was in focus at each different height level. So as the first scientist that wrote a paper about measuring roughness was with a microscope. Now we do it The same method today, but without all the sketching. So now we have these CCD array cameras that are like 27 megapixels. I don't know how many they are. They're huge though. Fancy cameras. And also, if you focus that light that's going down through a pinhole, it actually limits that focal range even more. So they'll have this light focus through a pinhole, and they'll get a map, and then they'll come up, they'll make a map, they'll come up, they'll stitch all those together, and they'll get a topographical map of the surface, a three-dimensional map of the surface. So they've got a picture of a rough surface now. Picture's worth 1,000 words, right? How do you control a manufacturing process with 1,000 words? That's tough. So when we take that picture, however we generated the picture, another way to do it is you take, you guys have all seen like old school record players. You know what I mean when I say record player? Does anybody know the physics of how that works? Yeah. There's a little needle, usually has a diamond tip on the needle, a very sharp tip on the diamond at the bottom of that needle, and it goes over a bunch of little bumps, and as it vibrates, it generates sound, because sound is just vibration, right? So you take a record player needle and you could drag it across the surface and see how much it goes up and down, and you could actually make a profile of that surface and learn how much it goes up and down, you know, in the area that's the width of that record player needle, which is pretty narrow, like 5 microns, 5 micrometers. So you could do that. You could take a laser, point it down to the surface, look at the reflected light from the laser and calculate how far away the surface was. And then you could scan that across the surface. So there's a bunch of different ways you can get these topographic height maps or profiles from the surface to measure when you're measuring roughness. But like I said, a picture's worth 1,000 words. I can't control my manufacturing process with 1,000 words, but I do know that I need to have a certain roughness for my part to function. So what do I do with my picture once I have it? Yes. You could compare it to known pictures, right? And people do this often. I was part of a study. They were trying to understand what our ancestors were eating. So they were taking fossilized teeth, measuring the surface of the fossilized teeth, and then they would take like an ape and observe their diet, then knock them out, make a replica of their tooth. Easier to do it if they're unconscious. Knock them out, make a replica of their tooth, and then measure that replica and compare the measurement of the ape's tooth with the measurement of the fossilized tooth. And the premise being that if they have the same kind of scratches on them, they were probably eating the same kind of foods. And so we actually took it. And so what they did at the beginning is grad students get to do all of the fun work. Who's thinking about grad school? Grad students get to do all of the fun lab work. So these grad students would sit for hours and hours and hours looking at pictures and circling little scratches and then counting the little scratches, and then with their little dividers measuring the scratches and be like, all right, this one has got so many scratches of this size, this one. And then they would do statistical analysis to find out that this animal was eating this. But that's kind of time consuming, huh? So we could compare the pictures. And we've done that, and we do that over and over again. What else could we do once I have that topographical map of the surface? So I could do math, right? I could analyze the signals. So who's a double E? Any double E's in here? No double E's in this class. But double E's do signal analysis all the time, right? They look at the different frequencies that come out of a signal and things. So we could look at the signal. We could do math and calculate parameters. Here's our surfaces, yeah. Again, big words, right? Surface metrology. This one is actually about the study of studying surfaces, though, I think. And so we have standards about this stuff too. So there's national and international standards about how to characterize. So there's an example of a topography on a surface. I don't remember what this surface is, but it looks an awful lot like a dinosaur footprint. We worked with anthropologists a lot. They would go like find fossilized dinosaur footprints, look at like the structure of the pads on the bottom of the dinosaur's foot because it was imprinted in the mud, and then compare that to the bottom of chickens' feet and stuff like that. Yes.
I'm sorry, this is a big tangent, but I was curious, what about it makes it look like a dinosaur?
I remember looking at the measurements of the dinosaur footprints. They're the little bumpy things on them. A lot of things have little bumpy things on them, but I remember we did that experiment. All right. So how does this matter to us in manufacturing? So here's an example of a profile on a surface. And here's a picture of the machine that measured the profile. So again, this is just a diamond stylus dragged across the surface. So what's the first thing that jumps out at you as you see this profile? This seems to be a regular pattern, right? It's going up and down and up and down. There seems to be some deviation from that regular pattern. So there's this up down that's pretty regular. And then there seems to be another wave inside there, right? Right. And so in surface metrology, we actually call that fine scale roughness, that up down stuff. We call that the roughness. And that other wave that we see in there, we're geniuses. We call that the waviness. And we can use mathematical filters to separate the waviness out of the roughness. So we say, all right, I only care about how rough, and you could imagine why that would be important, right? So like when you're walking down the sidewalk, Worcester sidewalks are a bad example. Imagine a sidewalk that you could walk down that would be smooth to you. And imagine an ant walking down the same sidewalk, right? So the ant interacts with the sidewalk on a different scale than you do. So the sidewalk is much rougher to the ant than it is to you. And so we can use these different wavelengths to separate that out. There's other ways that we also pay attention to the different scales of metrology, but we can call it surface roughness, waviness, and lay. Who's ever had Lay's potato chips? The roughly kind with the ridges? Just the smooth kind? Yeah, but you know what I mean with the roughly kind? So the lay is that directionality you see on the surface. So if you see a plowed field, all the rows lined up with each other, the lay is understandable because you can see the directionality on the surface. So this particular measurement was taken perpendicular to the lay. So it should show the maximum amount of roughness on the surface. Anybody guess what the part is? Let's go back to our manufacturing processes here. I know what the part is because I made the measurement. But so yesterday we were talking about if we wanted to make this fillet, we could take a ball end mill and we could step down the surface, right? And then the surface left over would be a bunch of scallops going down around that curve. So let's think, so in a milling operation, so we could get a surface that looks sort of like this by measuring around that fillet that we machined with our ball end mill. So if we did that, our surface wouldn't tend to be a little bit wavy and go up, right? Our surface would have that curve in it, right? And we don't see that curve, so it's probably not a fillet made with a ball end mill. Oh, just for scale, that's 5 millimeters long, 5.5 millimeters long, and 10 going to say 10 micrometers tall. So micrometer is a thousandth of a millimeter. So how else might I have made that surface? We've seen this picture, right? Where we've got our cutting tool here, and we're rotating like this, and we're feeding like this. So it doesn't actually leave that geometrically smooth surface that I showed there, right? Right? What it does is it leaves little scallops as it moves across. The distance between any two of them is equal to the feed as long as you use the units distance per revolution in the feed, right? Distance between any two of those scallops is the feed. Could you figure out mathematically what the height of each scallop is? Could you envision the math? I'm not saying do it today. I'm not saying whip out your paper. Could you envision the math to find out what the scallop height is? Really? All right, you do. All right. So what would you have to know in order to figure out the scallop height? What do you have enough information if I tell you the feed? No. Okay, so what other information do you need in order to figure out the scallop height? Yep. So you want to know the initial diameter, which I guess we measure over here, right? So diameter original, diameter final. Let's say you don't need to know that. Yes. So you want to know the angle of the cutting tool here. So the side edge cutting angle. That may be important if the feed is above a certain limit. But it's not important as long as the feed stays below that limit. Yeah. You need to know the radius of the tip of the tool. If you know the feed rate and the radius of the tip of the tool, you can mathematically calculate what the peak to valley roughness will be on that surface. Will your estimate be exact? Will it be perfectly correct? No, because there's going to be some vibrations that happen while the cutting process is happening, right? You hear noise when you do a turning process, don't you? So if you hear noise, there's got to be some vibration going on because noise comes from vibration. So there's going to be some vibration going on. There could be, the material could be less than homogeneous. So there could be spots that are a little bit harder, a little bit less hard as you go through, and that'll affect the cutting force, which will affect the deflection. Will affect the deflection. So if you know the tool nose radius and the feed rate, you can estimate the surface roughness, right? Because what you're doing is you're trying to figure out the You're trying to figure out the chord height. It's just the math for that chord height, right? And so if the feed rate is more than 2 times the radius, I think that's when we get a surface that looks more like I don't think we need, we don't need the angle then either. But the formula breaks down at that point. All right, peak to valley. Oh, so we get these surface roughness parameters. We can calculate a lot of them, right? So we just showed that we have this peak to valley roughness. So it's the toppity top to the bottomy bottom. You could also have the average depth of the valleys. You could ignore the peaks and just measure the valleys. You could ignore the valleys and just measure the tops. To make any of these, you have to figure out what's the mean value, right? And so you'll notice that our profile went uphill a little bit in the last image. So what we do is we take a best fit line. So we find out the line that on average fits that the best. We subtract that value, and now it makes it level and the mean value equal to 0. And then we can do all this other math to calculate these different parameters. There are literally hundreds of standardized parameters. This means you as the designer could specify, I want an RT of this, I want an RZ of that, I want an RA. RA is the average peak to valley height. RA is the average peak to valley height. So you take all the the average height of each point in the profile from the mean line. RQ is the RMS, so the root mean square of every point. And these are the most common roughness values that you'll see in industry. If somebody says the roughness is 10, or I need a surface finish of 15, then they mean 15 thousandths if it's America, and they mean RA. If they say that in Europe or Asia, then if they're working from a US print, they might mean that again, but they're probably working from an ISO print, which means they're measuring RQ, and it's micrometers, so 1,000th of a millimeter. These are the most common ones. They're not necessarily the most useful if you're trying to understand what's causing things, right? All three of these surfaces could have the same RQ or RA. They certainly wouldn't all perform the same in different areas. If I was making a seat, I might want this surface. If I was making something that was going to have high friction, I might want that surface. And if I was trying to impale somebody, I might want that surface. So you could have different surface values. All right, thousands of parameters. As the designer, you have to decide which ones are important to you. So the most common way that these are measured is not with the thumbnail, it's with the stylus profiler, although that may be going out at some point. It's important to note that when you drag your record player needle across the surface, it interacts with the surface. So just like when we were saying we have part-to-part variation for our manufactured parts, and we have measurement-to-measurement variation, the measurement itself affects the part. In this case, so this is hardened aircraft aluminum with a 5 micron. I think the radius of the diamond was 5 microns, and the scale bar there is 5 microns. So this was dragging that record player needle across to make a surface. And you can see that we also machined the surface with our record player needle. You can never actually measure the surface. You can only measure the interaction of your instrument with the surface. Yeah, this is an example of filtering the waviness. So that's the profile that we had the picture of before. It's been leveled. We take that long wavelength out, and we're left with that roughness profile. By changing the filtering parameters, we can change the measured values by 41% for RA. So if you're specifying RA on your print, it's not sufficient. You also need to specify how to do the filtering to separate the waviness from the roughness. Yeah, and we talked about quality inspection versus process control, right? That's all stuff we've talked about before. So, do you know more now about manufacturing metrology than you did before? Sweet. I think I'm good. We got 5 minutes early today. That's to make up for all the times I went 5 minutes over. See you guys tomorrow. Tomorrow we're talking about GD&T. Tomorrow's going to be GD&T, geometric dimensioning and tolerancing. So it's how do we put all this together and put it on our design so that we can make the part.